Okay, so if you've never seen a tether car, you gotta check this out. This is a video I found on YouTube of a tether car streamliner going at 205 miles per hour. I'll put a link to it down below, but check this out. So basically, they start these cars up. There's a person in the middle here who is spinning around with this car on like a thin line, and there's a tracker here which, you know, gets the speed of this thing, and you can just hear it speeding up and speeding up and speeding up. You see a little bit of a dust cloud starting to appear here too as it just goes faster and faster and faster and faster. And the entire goal of this is to just get these things going as fast as possible, just more speed. And then we cap out right there at that 205, and then they'll start to pull it back down. So in our practice problem we have here for this unit, this is practice problem 14.4. We've got a tether car here, but not on a tether, on a rigid horizontal rod. And ours isn't going to go as fast as 205 miles per hour. Ours is only going to go 7.9 meters per second. But notice here that while this tether car, you know, our toy car here, has a top speed of 7.9 meters per second, this is a linear velocity. It's meters per second. It's what we've been using, you know, before this unit the entirety of the year. It's meters per second. It's a linear velocity. So we tether it to the pole, and we let it drive in the circle as we kind of saw in the video. Now, the rod that we've attached it to is 1.8 meters long. So what we have here is, here's like the center of the pole. The rod is 1.8 meters in radius, and then our car is going to go around in a circle. You know, probably a better drawn circle than that one, but a circle nonetheless, okay? So this velocity that we have here is a tangential velocity. If we do draw a slightly better circle, this tangential velocity is the velocity tangent to this curve. It is the linear velocity here. We're looking for two things. How long, so a time, does it take for the car to complete one revolution, to go around one cycle? And then for part B, what's the angular velocity here? So we're looking for how long, which is a time, and then we're looking for an angular velocity, which is an omega. So let's try to figure this out. Well, if we're looking for a time and all we have is a linear velocity, v, we need to start thinking about how we can solve for time with linear components. Earlier on in the year, we learned that a displacement equals a velocity divided by time, which means, rearranging this, we could say here that time is just equal to wait, what am I doing? I wrote that wrong. Ugh. Look at this. What am I doing? A displacement is a velocity multiplied by a time. Look at that. You know, even physicists sometimes mess up their own work. So we know here in this case then that time can be equal to some displacement divided by a velocity. But this x up here, this is a linear distance or a displacement, okay, depending on if you're thinking this is vectors or not. Which, we're not using the letter x in our rotational unit here. We're using the letter s, because while this is a linear distance, it could be along a curve, whoop, for the circle. So if we could figure out what linear distance is traveled by the car in one circle, in one cycle, one revolution, and we divide that by the velocity, we can get a time. Well, if we're going through one revolution, what is the linear distance of one loop? Well, that's the circumference. And we can say that this linear distance equals theta times r, and for a circumference, we know that to be exactly 2 pi, it's 2 pi radians in a circle, multiplied by the radius of 1.8 meters. So when we run this math here, 2 pi times 1.8 gives us this linear distance, and we find here that the linear distance is about 11.3 or 11.31 if you want to carry it, meters. Note, even though this 2 pi is in radians and this 1.8 is in meters, we don't have rad meters. That's not a unit. That's not a thing. Radians is not a true physical unit. It's a descriptor to tell us, you know, how much of a circle or revolution have we gone through. So we don't carry this radian. It goes away. We just have meters here. This is our physical linear distance. So now we can just say that time here equals this physical linear distance, the 11.3 meters, divided by that top velocity of 7.9 meters per second. We see here that the meters are going to divide out, which is nice. The seconds is the denominator of our denominator, which brings it up into the numerator again, and we get 1.4 or 1.43 seconds. If you've been watching any of these videos, you know I'm not a huge stickler on sig figs, so we'll just say 1.43 and call it that, okay? So that is the amount of time it takes for our tether car here to make one cycle at top speed. Now for part B, we're looking for the angular velocity. We're looking for part B for an omega. Well, an angular velocity by definition is some amount of angular displacement divided by a time. So we could write it as a theta divided by a time. Well, if we've made one complete loop around the circle, that's 2 pi radians. And then when we divide that by the time, we know how long it takes to do that. 1.43 seconds. This gives us a unit of radians per second, which is what we're looking for. And we've got two options here. We can either leave our answer in terms of pi units. So what I mean by that is if we do 2 divided by 1.43, we'd have an answer of like 1.39 or 1.4 pi radian per second. Or if you wanted to, you could multiply that by that pi. And if we multiply it by that pi, we'd get something like 4.4 radians per second. Both are, you know, equal to one another. They are synonymous. They are the same thing. Typically, when we're talking about angular quantities, leaving that pi is often done if you don't want to deal with the calculator. Sometimes, you know, it's easier for us just to multiply it by pi and get the number. But those, either way, are two answers for our angular velocities of our tether car that we have in this problem. But yeah, you can get them going way, way, way faster than what we have here. And another interesting thing about this is that if you have a larger track, then it might take that tether car more time to get around it, even if it's moving faster. And as a result, two tether cars could have similar angular velocities, depending on that track, but their linear velocities might be very, very different. Okay? So just kind of an interesting problem here. With that, though, this is finished. Until next time, adios, and take it easy.